EOL CGD Seminar. I'm Sarah Woods, and on behalf of EOL and CGD, I'm pleased to introduce our own Dr. Kruse. Dr. Kruse achieved his bachelor's from University of North Dakota before pursuing a master's in atmospheric science from the University of Wyoming and a doctorate in geology and geophysics from Yale University. His graduate studies focused on mountain wave propagation and attenuation and their influences on Earth's atmosphere and involved participation in the EOL deep wave, deep propagating gravity waves experiment. From Yale, Dr. Kruse joined the Advanced Study Program at NCAR before joining CGD as a project scientist, where he worked to quantify errors in the community atmosphere model via nudging experiments. Dr. Kruse joined nearby Northwest Research Associates in 2021, where he used machine learning to predict latent heating profiles from weather radar data and set up custom configurations of WRF to accept these heating and compared simulations to AIR's satellite data. After Northwest Research Associates, Dr. Kruse joined SciTech in Boulder, where he worked to improve infrared satellite data processing algorithms for real-time object detection and tracking. Most recently, Dr. Kruse joined us at the Research Aviation Facility in July, where he takes on responsibility for producing high-quality wind measurements from the NSF G5 and C-130 aircraft. I think I can honestly say Chris is excited to re-engage his gravity wave research in his new project scientist role. On that note, please join me in welcoming Dr. Kruse for his seminar on evaluating gravity wave drag parameterizations.
Thank you very much for that introduction. So today I'll be talking about what Sarah just said, evaluating gravity wave drag parameterizations using wave resolving simulations of actual observed events. So to get started really basic, what are gravity waves? Gravity waves are nothing more than buoyancy oscillations that can happen in stably stratified fluids. This is a very familiar example to most people. Here you throw a rock into a pond. You've got very dense water under very much less dense air. And this mechanical perturbation sets off a wave, which then propagates outward from there. Within the atmosphere, there are many types of sources. Basically, any mechanical or thermal perturbation can set off a wave. But we generally consider there to be 4 primary sources of waves. We've got mountains, which we're quite familiar with here. There's deep convection, where the diabatic heating is a significant driver. There's imbalances associated with jets and fronts, and even vortex instabilities. And then shear instabilities as well can all be sources of waves, in addition to other more exotic sources. In terms of weather and climate models, though, these are the 3 sources that tend to be parameterized. And within this talk, I'll be focusing on the left-hand side, mountains and convection. So as kind of alluded to in the previous slide, gravity waves, we generally consider their sources to be in the troposphere. Really, gravity waves can propagate in any direction, and they can be generated pretty much at any altitude. But we generally consider the sources to be in the troposphere, and from there, we're interested in when they propagate upward. When they propagate upward, in order to conserve, say, for example, momentum, as density decreases, amplitude has to grow. So as you see in this cartoon, waves are going up, and as they go up, they grow in amplitude with decreasing density. Then aloft, they eventually have to break. These, as they grow in amplitude, you're going to ultimately excite some sort of instability, either overturning, like crashing on a beach, or shear instabilities, and those waves will break down. We're interested in these waves because they transport energy and momentum, and it's where these waves break that you deposit this energy and momentum, and it's the momentum deposition in particular that we tend to represent within weather and climate models. So here's a single slide on impacts of gravity waves in climate, which doesn't really do the topic justice. This could be its own seminar. Here I'm showing 2 Wacom simulations. It's zonal and time mean zonal winds. And here's a simulation with gravity waves, and this is northern hemisphere winter mean, southern hemisphere winter mean. And here's what the simulation does when you do not have the gravity wave, any gravity wave drag parameterization. You get huge impacts. Broadly, roughly, gravity wave impacts increase with altitude as you decrease density. Impacts are both direct via their direct momentum deposition and forcing of the momentum equation, but also indirect via interaction with Rossby and planetary scale waves. But to summarize, they have huge impacts in the mesosphere, as you can see by comparing the upper sections of these plots and the huge differences. In the stratosphere, there's both important direct and indirect impacts. There's direct forcing of the QBO, for example, direct and indirect forcing of the Brewer-Dobson circulation, and then, at least in the zonal mean context as well, there's influences from the stratosphere down into the troposphere, which are influenced by these parameterizations as well. So gravity waves, though, are relatively small scale. They span all of the mesoscale, but the smaller end of the spectrum can be really important. And this is an example of, mountain waves, orographic gravity waves. So, for example, if we have about a 100-kilometer resolution grid over this complex terrain of New Zealand, you can see all of these small-scale terrain features. And these small scales are what ultimately force mountain waves. So climate models are obviously going to need to parameterize all of this subgrid scale variability and their influences. However, even weather models, which have an order of magnitude higher horizontal resolution, still have effective resolutions on the order of 80 kilometers or so. And so you're going to be missing a lot of this variability in a lot of the waves that it generates. So parameterizations are used in basically all weather and climate models. However, these parameterizations are still pretty idealized, far more idealized than current understanding. It's not true for all parameterizations, but roughly they often consider only vertical propagation. They use a column approximation. Often they're only representing a single horizontal scale, when in reality you have many, if not a continuous spectrum. You consider steady theory, which means that you're effectively assuming infinite group velocities and more. And unfortunately, while there's lots of platforms that you can get good observations of gravity waves with, these data are still not quite good enough to really well constrain the parameterizations. Aircraft and superpressure balloons, in terms of mobile platforms, produce really, really good data. But unfortunately, as we were seeing, the higher you go, the more important this process is. But both of these platforms are kind of topped out at about 20 kilometers. Satellite data are really good. You've got global coverage, but you've got downsides as well. There's limited horizontal resolution. There's really limited vertical resolution and a lot of vertical averaging. And so you can make use of the data, but you're still missing a lot in terms of these fields. And I'm not showing ground-based stuff, but ground-based observations also exist. But one measurement in one location is kind of hard to use if you're thinking about parameterizations over the entire planet. So within this talk, I'm really wanting to focus on this upper level region, the stratosphere and mesosphere, where these waves are breaking and having a significant impact. So the overall objective of this talk is to try to evaluate parameterizations against data. Given the altitude of interest, I'm really wanting to use the AIRS observations, which is an infrared radiometer that gets you radiation from a number of different wavelengths. But the channels of interest, there's still drawbacks with this measurement platform. You've got limited horizontal resolution, though that's pretty good. You've got significant vertical averaging. This is the vertical observational filter that effectively gets applied by taking these observations. So you have enormous vertical averaging, and you only get 2 measurements per day for this particular instrument. And we want to go all the way through to what kind of drags are we getting within the parameterizations. So to bridge that gap, my approach within this talk is to use gravity wave resolving models that are in realistic configurations using all physical parameterizations to validate these parameterizations against data in order to kind of bridge the gap from incomplete observations all the way through to the parameterizations. And one thing I'll note here is that deep realistic modeling requires good boundary conditions. But good boundary conditions to a very high altitude is a relatively new development within atmospheric science. It's really about circa 2010 that weather prediction models and reanalyses were extended up to these altitudes that allow you to then force realistic cases. So why this is now possible, are these models accurate within the stratosphere and mesosphere? So within this talk, I'm going to be showing results from 2 recent papers. And so this first, here's the first paper, and the first topic really is mountain waves. So we're looking at observing and modeling mountain waves throughout these altitude regions over the Drake Passage area. This project came about as part of an International Space Science Institute team that was organized by Joan Alexander just across the street. This project brought together this great group of people with expertise in satellite observations, in weather prediction, in climate modeling, and parameterization development, and it was really a great group of people to bring together to study this particular topic. And here, the overall objective was to try and produce new quantitative constraints on mountain wave drag parameterizations. We were interested in the Drake Passage region because we wanted to use AIRS data, as I was previously mentioning, and at least according to what waves AIRS can see, the Drake Passage region is kind of, and really it's the southern Andes, is a global hotspot. You've got various mountain ranges that produce lots of mountain waves. In the northern hemisphere, there's there's fewer regions in the southern hemisphere, but the southern Andes really are the global hotspot in terms of what this instrument can actually see. So we wanted to look at that area. So within this study, there were 4 models that participated. There was WRF contributed by myself and the Met Office Unified Model. Both of these were run in a regional configuration at 3-kilometer resolution, trying to resolve fully, as much as possible, the mountain wave spectrum and the forcing spectra. There was also the ECMW of IFS at 9-kilometer resolution and ICON at 13 kilometers. And these were run in their operational configurations of the time. All of the models were deep. This is a unique aspect. They all had tops at 1 Pascal, or about 80 kilometers. This was really important because as we see these observational filters from the AIRS instrument, we really wanted to contain as much of these within the model domains as possible and not have much of it be where we have the artificial upper damping. That way we can have quantitative apples-to-apples comparisons between the modeling and the observations. So we decided to simulate a 10-day period with all 4 of these models because there were lots of mountain wave cases, and all of these models were initialized and guided by the same IFS analyses. So here's some of the data. These are the AIRS overpasses during this 10-day period. There ended up being 24 overpasses where you could see mountain waves within the data, and I'm only highlighting the regions that were contained within all of the model domains, really, contained within the 2 regional models. So we've got waves coming off of the Antarctic Peninsula, waves coming off of the southern Andes, as expected, but we also had cases where we had waves coming off of the smaller South Georgia Island to the east. And all of these data that you see were used in all model validations. So in order to compare the model to the observations, this was quite challenging, quite a lot of work, mostly done by Lars Hoffman, pictured here. So essentially what we did is we created synthetic AIRS data from these 4-dimensional model fields. So what he did is he took into account observation time, he took into account viewing geometry of every individual footprint, and these brightness temperature products that he's producing are averages of collections of channels. He simulated the radiative transfer of each one of these individual channels, and then with the ultimate objective of producing synthetic data in the same form that he gets when he processes real data. So everything is done apples to apples, and the same algorithms that are applied to real data are applied to the synthetic data. So here are some comparisons between between the four models and the observations. Observations are upper left. In this case, we're looking at this 15 micron high brightness temperature product. It's only an average of 2 channels, so you do see lots of noise. But in this case, you've got large amplitude waves coming off of the southern Andes. And really encouragingly, the higher resolution models produce waves that are quite similar in character to what we see in the observations, minus the noise. And really encouragingly, also the coarser 10-kilometer resolution models also seem to well represent this case. So this was, I'd say, an overall remarkable comparison where all of the models seem to give us a really good agreement compared to the data. Here's another comparison of mountain waves coming off of the Antarctic Peninsula. Again, data upper left. Here, the higher resolution models give really good comparisons with the data. Obviously, there are some differences, but overall, you see a really nice comparison with the data. However, the coarser models here, in this case, don't do as well, presumably because these are smaller scales that are on the edge of what is represented and maybe not really represented given the horizontal resolutions. But overall, at least for the higher resolution models, again, pretty good comparisons compared to the data. Well, we can look at all of those overpasses. We'd like to be a little bit more statistical. So here's an evaluation of wave amplitude, or it's just brightness temperature variability as a function of scale. 2D spectra for each overpass binned into one-dimensional spectra, and then summed over all overpasses gives us a single one-dimensional spectrum for all 24 of those overpasses. And here we see data, and then all of the model curves as well. So the higher resolution WRF and overall do pretty good at representing the brightness temperature variability that was observed. Though if you only look at the scales that are unaffected by noise and unaffected by numerical dissipation, because you can see these tail-offs, even ruling out those scales, all of the models still underrepresented amplitudes or the brightness temperature variability by about 10 to 30%, with the higher resolution models being in the 10% range. So not perfect, but at least we're talking about tens of percent instead of hundreds of percent. So finally getting into some highlights of the science, here's a result of comparing the different models. And here I'm showing momentum flux cospectra over these 3 different subregions, over the southern Andes, Antarctic Peninsula, and South Georgia. And these spectra are plotted in a way that the area integral in the space plotted is proportional to the momentum flux. You see 2 groups of curves. The 10-kilometer models have larger scale waves, but going to higher resolution, you resolve these smaller scales, and these smaller scales do flux a lot of momentum. And roughly by eye, even more so over South Georgia, going to these higher resolutions, you get lots more momentum flux, and this is suggesting that even at 10-kilometer resolution, weather prediction models are still needing to parameterize a significant percentage of the momentum flux. Another takeaway here is that momentum flux spectra are broad, which is not surprising, but it's good to remind ourselves, and parameterizations usually represent one scale. So here, I wanted to compare the higher resolution models to the parameterization. So in all of these plots, all I want to compare are the red and blue curves from WRF and to this brownish reddish curve, which is a curve from the current parameterization within NCAR's community atmosphere model. Here we're looking at vertical fluxes of horizontal momentum in terms of momentum flux, and the drag that is inferred from the vertical derivative of those profiles. And one result that was apparent in all of the subdomains, not just these 2, was that we kind of saw that there was too much drag at too low of an altitude. Over the Andes, that's not so much an issue of magnitude, of amplitude. Over the Antarctic Peninsula, you see this even more so. So in terms of the parameterizations, you've got too much drag at too low of an altitude, and then not very much drag aloft, in contrast to the wave resolving simulations that are well validated, that show generally large and increasing drags as you go further aloft. So this was one result over all of the regions, and now I'm going to speculate as to why. I think one of the reasons why this might be possibly a trend within these simulations is that the parameterization, while this one does represent scale to an extent, it does represent orientation, it does not represent lateral spreading of momentum or of mountain waves with height. Whereas in reality, here we're looking at idealized simulation of mountain waves coming off of this little bump at 65 kilometers. The waves do spread out. And this lateral spreading can reduce the amplitude relative to what you would predict if you did not account for it. And that's really highlighted on the right-hand side, where this gray curve is a prediction of amplitude as a function of height. And this black line is a threshold at which you would get wave breaking according to linear theory. And the gray line is for 2D theory that does not account for the lateral spreading. However, all of these different curves correspond to different three-dimensional topographies going from ridge-like to ridge parallel to the flow. For example, if you have 2D ridge, like true 2D theory, you might predict breaking at about 40 kilometers, but if you have an isotropic terrain, the lateral spreading, linear theory predicts that you would get breaking closer to 80 kilometers. So this lateral spreading can have a huge effect on breaking altitudes. Another gravity wave phenomenon that can happen that is not represented within any parameterization currently, I think, is spectral and transient influences. If you've got an isolated bump, you've always got a spectrum of scales that you're forcing. That gives you a spectrum of vertical group velocities. And linear theory tells us that, short waves will propagate up quickly, long waves propagate slowly. And so this can lead to vertical dispersion of the wave activity and spread out drags further aloft. And so this is an idealized wharf simulation. Here's momentum flux as a function of height and time. And here's the corresponding result of the drag. This is the total delta U, which is just the time integral of the drag. This is all in contrast to the parameterizations, which use steady theory. Even if they're spectral, all waves propagate up instantaneously. You immediately attain your maximum amplitude, which breaks at a lower altitude. And the result is you tend to have drag confined to too low an altitude as well. So this is another effect that I think happens in reality that is not represented and might be one of the reasons why we see too much drag at too low an altitude and too little further aloft. And the final result that I'll highlight from this paper is looking at the meridional drags. So really just focusing on these central profiles. Again, this is profiles that have been area averaged and time averaged over that entire 10-day period over the region of interest. Here we're looking at the South Georgia Island with this northwest-southeast oriented terrain. In terms of the parameterization, again, we're seeing too much drag at too low an altitude. And I think this could be, in effect, due to the amplitude might be too large. That's certainly suggested from the momentum flux profiles, but also maybe no geometric spreading. However, you still get drag, southward drag, that looks similar even if it's misplaced in altitude. It's similar to what we see in the wave resolving models. But the curious result here in the wave resolving models is that we get a complete reversal of the forcing by the mountain waves. And so what I think is happening here is shown on right. So if we have winds from the west, we might get a wave field like this from an isolated terrain. We're going to have north-south oriented phase lines, but we'll have this southern wake and this northern wake. As you go up in altitude, and if you rotate the winds to the clockwise, which is what we're seeing in this case, the winds become more and more parallel to the phase lines that were forced on the southern side. And linear theory predicts that these waves will, their vertical wavelength will become 0, their steepness will grow. Long story short, linear theory predicts that these waves should break and they should go away. So where we've got the strong meridional shear is where we have the strong southward drag, and so this southward flank, which we're kind of seeing here, is probably getting attenuated. But the northward flank is still propagating up, still growing in amplitude, and it will eventually break, and it will have the opposite sign in terms of drag, which I believe is what's happening here. So this is another effect that is represented to an extent with an NCARS model, but the only way you can really represent this is to have not only some sort of spectral representation of the mountains, but there has to be a two-dimensional spectral representation of the mountains in order to get that effect represented. So now moving on to convection-generated gravity waves. So here are some results from a paper published earlier this year, where I was trying to do something similar with convection-generated gravity waves. Convection is a really significant source of gravity waves, particularly in the tropics, and these gravity waves are really, really important, a significant driver of, for example, QBO. While very important, they're really challenging to study observationally. We can use models just like I did before, but when it comes to convection, models never get convection in the right place at the right time. So while you can have convection and gravity waves coming off of them all within your model, it's hard to compare these models quantitatively to what few observations exist. So within this paper, essentially what we're trying to do is use radar observations to inject thunderstorms and thunderstorm forcing into a weather model. So the whole idea is we start with weather radar observations. From the weather radar observations, we want to predict convective diabatic heating. And then we put this convective diabatic heating into a weather model, and we let it respond in all the ways the dynamical core and resolution allow. And so that's what we are seeing in this video. We've got convection on the left. The diabatic heating is not shown. And then here's the mid-tropospheric vertical velocities. So you have convective updrafts, compensating subsidence. You do see tropospheric waves radiating outward from there. But we hope that this will allow us to model the waves that come up realistically. And in order to go from radar variables to diabatic heating, we use two different learning methods, one of which is a neural network. So in order to predict Q, we want to, again, use radar observed quantities and predict Q. While we have radar observed quantities of convection, we don't have diabatic heating. So to try to get at that, we used realistic simulations of WRF. And so there we have simulated radar quantities, and we have the diabatic heating, and we're using two learning methods to make that prediction. In terms of training data sets, there's two. There's one of deep tropical convection near Darwin, Australia. That was from a previous study. And then I also did some simulations of unremarkable subtropical convection over Florida. In terms of the two methods, we used a lookup table, which is essentially just binning diabatic heating profiles and averaging them over rain rate and ecotop height bins. And then developed as part of this work, I trained neural networks to take in those same input variables estimated from radar, as well as reflectivities at 3 different levels. So how well do these methods predict diabatic heating? So one thing I'll mention is that the lookup table, which is just this averaging or compositing, was only trained on the Darwin simulations. Given these two simulations, though, I trained up 3 neural networks, one on Darwin run only, one on the Florida run only, and one using both simulations. And here we're testing against data that was withheld from the Florida runs. So for every grid cell, we've got those input variables, and we've got a single diabatic heating profile, and we're just trying to make a prediction of that. On the right, these are profiles of bias in solid and mean absolute error in dashed for the 4 different methods. And the solid line is the average diabatic heating as a function of height. So you can get a sense for how big these biases and errors are relative to what is typical. And these are for moderately convective and more strongly convective grid cells. So focusing on the stronger convective grid cells, the lookup table and the neural network, both trained on the Darwin data, are shown in red and blue. They have similar skill in terms of biases and mean absolute errors. However, if I train the neural network on the Florida data and also test against Florida data, the more representative data significantly reduces the biases and mean absolute errors. What's really interesting here is that if you go further and then add in the Darwin data as well, you still get further skill at predicting diabatic heating for the Florida region. So the takeaway from this is neural networks have similar skill to the lookup table method, but they do allow you to use more readily other types of data, and the more representative data, the better when it comes to training data, and the more data in general, the better. So we can predict these diabatic heatings, but can we put that into the model, and will we get something similar to what we see in observations? So we decided to find a case which appeared to be convection-generated gravity waves over the Florida region. So we found these two overpasses from the same time with two different, from these two different brightness temperature products. We see these smaller scale features with, it's kind of hard to see, but you can see these kind of concentric rings which appear to be convection-generated gravity waves off to the east. If we looked at the reflectivity from the weather radar network, we have this loop on the bottom. So this is over the 6 hours prior to this overpass. So we do in fact see two blobs of convection, one over north central Florida and one over the southeast of the United States. So it's looking like these are in fact convection-generated gravity waves. So we went ahead and took these radar data, took the Darwin and Florida trained neural network and predicted diabatic heating and put it into a model. So in terms of the model, it was very idealized. 2 kilometer resolution in the horizontal, 700 meter in the vertical. It was deep to 80 kilometers again, so we can compare with these AIRS observations. And it's kind of comical how simple this model was. It's dry. There's no physical parameterizations. There's no land-sea contrast. There's no topography. There's nothing. Nothing, in fact, would happen within the model if we didn't perturb it. The only forcing that is applied to the model is the predicted diabatic heating. So we pulled this profile out from Merit 2. We calculated the diabatic heating every 2 minutes, updated that within the model every 2 minutes, and then simulated this case. So here's what some of the raw model output looked like for this particular event. Reflectivity is on the left. I think this is 2-minute resolution. And we've got temperature perturbations at 30 and 60 kilometers in middle and right. As the convection gets going, you do start to see all kinds of wave activity coming off of the convection. And things get more and more dramatic as you go higher in altitude. But at first glance, we see waves kind of where we expect to see them. And then the other thing to note is while the convection is quite localized in space, you see these waves do kind of ring out and propagate to very large distances away from the source regions. So here, so that's what's actually happening within the model, but we want to compare it to the observations. So in order to compare it to the observations, I took the output that was closest to the overpass time of the data. And then I went ahead and applied both the horizontal and vertical observational filters. So there's some horizontal smoothing and significant vertical smoothing to the model. And we end up with this comparison. Data's on the left, and our synthetic AIRS observations are seen on the right-hand side. There's a lot of differences, but at least it's pretty encouraging. You see these blobs of small-scale features over the regions of convection, and you do see these regions of concentric rings coming off to the east. And that does look to be pretty similar to the data, even though the data is quite noisy. There's other differences, like these waves that you see up here, and those are not in the model, but that's fine because that's from convection from a previous day over the Midwest. that's not represented in the model. There's also not noise in the model, which is convenient. But overall, there's pretty good quantitative agreement. And in this case, this is the same color bar is shown for both the data and the model results. So the agreement is kind of quantitative. So in terms of results, I'll just show one result in terms of the gravity waves. Here I'm showing U amplitude and W amplitude and the two components of gravity wave drag over the entire domain, averaging in the zonal direction and averaging in time over the 30-hour period. These contours are showing time and zonal averaged diabatic heating of 1, 6, and 12 Kelvin per day, kind of showing where the convection, the actual heating was within the model. You see the largest amplitudes over the largest diabatic heating, but what you also see again is this lateral propagation, the spreading with height of the waves. And it's not too surprising. We already saw that in the actual simulation, in the raw data. But when we look at the drags, what's kind of interesting is despite this localized diabatic heating, the drags themselves that are responsible for they are the body forces that will be applied by the small scales onto the larger scales. They're kind of invariant in latitude, despite the pretty localized forcing. So again, this is highlighting the importance of lateral propagation and showing that not only do these waves propagate far, when they do, their drags are almost as significant as the drags directly above. And this is in contrast to the way this is handled in parameterizations. Parameterizations still are vertical only. They don't take into account lateral propagation, especially even for convection-generated gravity waves, as far as I know. So if you have these regions of convection within this particular grid box, instead of getting all of this spread with height, which has important impacts, everything would be confined within a particular grid cell. So with that, I'll summarize and just say, when it comes to this relatively new capability to run models to very high altitudes, if you can well characterize the forcings, the sources of these gravity waves, gravity wave resolving models can do a pretty darn good job at reproducing what we actually see from observations. And this is true for both mountains and convection. And this is encouraging because, as kind of highlighted here, these validated simulations highlight physics that are not completely unknown but less studied, that do seem to have impacts on where this process is going to have impacts within weather and climate models. So I won't go through this list, but these simulations do kind of provide motivation for paths forward. So with that, that's all I wanted to say, and thank you very much for your time.
Thanks, Chris. That was really interesting. Quick reminder for those online, there's a Slido box if you scroll down on your screen there that you can enter your questions and we'll read them off in the room. For those in the room, we have a new microphone today if you want to catch it, or you can go old school. Anyone have questions?
So where's the actual microphone?
He said it's already on. It's that
Oh,
big
okay.
black part on the top.
All right. Thanks, Chris. Yeah, that was really interesting. In the convection case, I didn't understand exactly how the cues look in time. Are they, do they have a lot of high frequencies in time?
So I don't have anything to show you too much, but I would say they kind of follow these regions of reflectivity, and they're as compact as you see in these regions of reflectivity. They're not very expansive, so what you see is kind of what you get in terms of reflectivity. And so where you see, sorry, I lost my mouse. There it is. Where you see, the more intense activity is where you see actually have more intense forcing within the model. In terms of the one plot that I do have for you, this is the time integral, so it's averaging. But here's the time integral and the vertical integral of diabatic heating. And so while you've got all of that convection kind of popping up all over the place, in this case, it really was this north-central Florida case, that blob, that was responsible for most of the heating. But yeah, so I don't know about the temporal variability, but we did update every 2 minutes within the model. So it's pretty high. We supplied it at a very high frequency.
Right.
Any other questions in the room? While they're pondering, I'm curious, so I know you have big interest in the upcoming CG Waves airborne campaign. I know you've done some work with Deep Wave. Do you have any specific plans of trying to incorporate some of the aircraft data to validate some of your results?
Yeah, so I didn't show it in Deep Wave. I did extensively use the aircraft data to do something similar. So that was very useful in the past, and there I used the in-situ wind observations. In terms of CG waves, I'm still kind of learning what the PIs want to do, and they really, I think, are focused on their upward pointing lidars, which will provide really excellent data of what we're seeing in these simulations. So I'd certainly be very interested to take a look at that, and I'm sure they have their own methods of doing something similar. I'd be really curious to see if their data agree with something like this, which I think is kind of the state of the art.
Sure.
While we're on the topic of airborne data, you and I have talked a little bit about old data sets potentially being useful for the work that you're doing. To what extent are there data sets available that would be helpful to this work, and some of the barriers to digesting that information and using it in your research?
Yeah, so I've taken a look at the last 20 years of aircraft data from RAF, and there's a lot of data out there, and I would say the in-situ wind observations are probably really, really useful. I think there's a whole bunch of gravity wave analyses that could be done that were not done already in the past. So I think there's a lot to be gained from additional analysis of previous data sets. Looking to the future, I still think the in-situ winds are extremely important, especially for anything orographic. It's like pure gold, but these upward pointing lidars being flown on the aircraft now are a really significant advancement in gravity wave science, so we can actually look at the regions where these waves are starting to explode and topple and force circulations.
All right, while the room ponders, we have a question online from Wampu. In MPAS with 3-kilometer resolution, do we need parameterization of gravity waves?
Yeah, thank you very much for that question. I would say kind of. You're at 2 to 3 kilometer resolution. There are some indications that you are still not resolving all of the spectra, or the whole gravity wave, mountain wave spectrum. Just thinking about mountain waves, that is. I think Ina Polichuk has a recent paper with ECMWF. She went down to 1 kilometers and found that I think the gravity wave drags and momentum fluxes did not converge all the way down to 1 kilometer. She went from like 9 to 3 to 1. So I would say, we're probably getting to the point that we're getting to 80 to 90% of the full gravity wave spectrum, but it's still not 100%. And going to higher resolution, you probably will see differences in the waves and the drags that they impart, even at 3 kilometer resolution. And within this study, we had 2 simulations at 3 kilometers. One was more dissipative. The was more dissipative than WRF. And as you go up in altitude, you see the effects in these spectra. And that was one of the reasons why there was less momentum flux at the smaller scales in compared to WRF. But that's a paper. That's a detail to look at in the paper. Short answer is you don't have everything even at 3 kilometers, even though you think you should be getting pretty close to 100%.
Good thought there. We have a couple more questions online. One from Jimmy. How easy or difficult would it be to represent these vertical radiating effects in a gravity wave drag scheme?
Yeah, I would think it's quite difficult. I know there have been some recent attempts in literature where people are, having a source in one area and accounting for vertical and horizontal propagation. But I think those were primarily orographic. And I don't know if anything was done with convection-generated gravity waves. In short, I think it's pretty difficult to do, but people are starting to head in this direction and actually have source and rays propagating as a function of time, and you're figuring out where they go and where they break, and you apply drags wherever it is that you predict that they'll break. So short answer is, yeah, it's difficult, but people are starting to do this even in a climate model context.
Great. Another question from online from Rich. What might the climatological impact be of convective gravity waves over Florida, for example, on the climatological flow? What would coarser models in general be missing here?
I don't know the answer to that. We only looked at Florida because we wanted as tropical as possible, but we still wanted the United States radar network. We really wanted to look in the actual tropics. So it's more of a, can we do this? And we did it where we have data. But yeah, I wish I could answer that question. It's a good one. I'd love to really focus in on, what are the drags and what are the impacts of these drags, and not just look at a regional scale, kind of think about what would be the global impact on, the QBO or whatever large scale circulation it is you're looking at. But let me just read that again to make sure I don't miss anything. Yeah, I mean, the coarser models, if they don't have the parameterizations, they're going to be missing the waves. So, yeah, I guess all the way to the beginning, it's coarse, this is all gravity waves, but it depends on the latitude that you're looking at, what kind of impact you might expect. I'll stop rambling about that.
Thanks, Chris. We have one more question online from Yuan Pu. Could you explain how you get Q from radar data?
Yeah, I went over that really fast. Essentially, we do this entirely within WRF. Within WRF, we have simulated radar quantities, but within WRF, we also have diabatic heating. We're doing this grid point by grid point. So for every grid point where you've got rain rates above a threshold, we used, I forget, what was it? It's like 1 millimeter per 10 minute. If we had more than 1 millimeter per 10 minute, we considered that a convective grid cell. For every grid cell, we had, all of this input data within the simulation, and also this input data from actual observations. So there we had this vector of rain rate, ecotop height, reflectivity at these 3 different altitudes, and we also had the diabatic heating. And then we just did a standard training of a neural network in order to predict that profile. So in short, we learn it from WRF, and once we learn it from WRF, we then feed it real data and hope that the result is realistic, even though everything was based on a model to begin with. But it seems to work fairly well.
Very neat. We have one more question online, but real quick, do you want to toss one more question from the room?
Good thing I stopped early.
Yeah, do you think you can learn machine learning or however about sources that you don't know about? That's one of the problems with parameterizations as they exist in vacuum, for example, that you have 2 or 3 important sources, but you probably don't.
Maybe. I mean, if you had a region of drag and you hypothesize that there are certain predictors for that drag, you could use machine learning and explainable AI techniques to determine which one of those input variables might be most important for representing drag at a particular altitude. So I don't know, that's one possibility that I could see. It would be saying these variables are very important, and then if you physically intuit that these variables are corresponding to this particular physical mechanism, then you could try and go backwards, I would say. But off the top of my head, that's one idea.
All right, we have a question in line from Minghui. Thanks for the great talk, Chris. Are there any plans at RAF to produce integrated observational data sets to study gravity waves, such as combining multiple in situ and remote sensing instruments on board an aircraft?
I guess short answer is no. No plans. But that would be very interesting. Yeah, no, I haven't. I personally haven't thought about that too much. I've primarily thought about the LiDAR data and the in situ ones, but integrating them, I suppose, with other upcoming observing systems, this could happen. So I'll certainly be taking note and following the progress.
Sounds great. We're lucky to have you on board to start thinking about these in the future. Do we have any other questions in the room? All right, then I wish everyone a happy Thanksgiving, and let's thank Chris one more time for that great talk.